I'll introduce Qian Wu. He is a project scientist with NCAR in the National Center of Atmospheric Research. His talk is entitled Understanding Space Weather and Thermospheric Wind in the Polar Region. So we're moving to space. And Dr. Wu is specializes in observations of mesospheric and thermospheric winds from balloon-borne, space-borne, and ground-based Fabry-Perot interferometer, or FPI, to study gravity waves and tides.
I'd like to thank the organizer inviting me here, give this talk here, and change gear a little bit. And instead of talking about stuff going on the ground, we're talking about something a little bit away from the ground. And I had a lot of collaborators, and here are a few involved with my Apollo projects. William Wu from University of New Brunswick, and my colleagues from Korean Apollo Research Institute. So here's an outline why we do care about space weather in the polar region, and why we need to know the thermosphere winds, which is since I do most research on, and what is the current status of the thermosphere wind instruments in the polar region, and what we're hoping to happen in the future. So why would we need to know about space weather in the polar region? And space weather usually starts with ionosphere disturbances in the polar region, and then propagate into mid-low latitudes. And space weather can be very disruptive to navigation and communication systems, and that's because all these signals either reflected or go through the ionosphere. And another thing to care about is that most of GPS or the space satellites are at the lower inclinations. And so when you're at the polar region, these signals are all coming from pretty low elevation angles. So you are more susceptible to the signal scintillations to those systems in there. And the goal of space weather research is to able to forecast ionosphere variations and to predict how fast, how far these things can travel to mid and low latitudes. So what is an ionosphere? An ionosphere, looking at this profile here, and you can see that it's really ionized gas, and mostly it's atomic oxygen in the thermosphere. And looking at this, and you can tell that even though we call it ionosphere, it's really a small percentage of the atomic oxygen ionized. You see it like a 3-order magnitude smaller. Majority of the neutrals still in there. So you call ionosphere, it's like 100% ions and electrons. It's not that. It's only a very small part of it. But even though it's a small part of it, it does have a large impact because some of the radio wave can propagate through, some can only be reflected. And so we care about those things. Another thing is that these things are produced by solar UV radiations, and during the day, and they live long enough. During the nighttime, they're still there and flying around. And another thing is that this is sort of like you have a kind of balance, chemical balance. You have the UV producing the ions. At the same time, these things interact with neutrals in the thermosphere. They constantly losing them. And the one of the species are really well known for recombine with ions is N2. It's a nitrogen gas. And so in this kind of balanced condition, if nothing changes, and if you think the sun is just a light bulb, that should be fine, nothing changes. But the sun does more than that, and the sun also spitting out plasmas, and we call it solar winds. And so they're traveling away from the sun, and the Earth has a magnetic field, and its dipole field look like. And these plasma clouds interact with its magnetic fields, and so we sort of like fly in this plasma cloud. And when everything's normal, usually this magnetic field is close to itself, and they're circulating within the system itself. We call it a magnetosphere. But when the solar wind magnetic field turns southward, we'll have a sort of reconnection. And so many more field lines will open to the solar winds. And when you have a plasma cloud passing through magnetic fields, it generates electric fields. So basically, you're just adding a sort of like a electric power source into the Earth system over the polar cap, where the field line connected to the solar winds. So here's a diagram shows you how this current goes through. And the space weather is really a big topic. 20 minutes really cannot cover all of them. It just cover a small aspect of it. You have a fields, you have a currents coming in, you have an electric field applied to the polar cap. And one thing it does is that you have a potential across the polar cap. You drive the ions, which is in the ionosphere, from the sunward direction, anti-sunward direction, to the anti-sunward direction. So you have an electric field applied to it, and then you have a magnetic field in the vertical direction. Then they'll drive the ions going through this direction here. And as we said earlier, the ions only a small part of it. And the thermosphere is still there and have a much higher density. So the ions have to go through the thermosphere in order to moving in the system here. So what it does two things. It transfers the energies into the thermosphere. And one is a group velocity, just transfer moving the thermosphere in a bulk velocity. Another one is generating a sort of random motion, what we call the geoheating. And you'll generate heat in there, in the thermosphere. So this is we at NCAR, which is doing a lot of a modeling effort. We have a model at NCAR, can simulate these kind of interactions, how this ionosphere interact with a thermosphere, and how the geoheating is happening during when the solar wind magnetic field turns southward. So this is a movie. Says most time it's pretty quiet, and once this happens, you can see that boom. There's a lot of heat generated in the polar cap. So what this does is it's like a stirring a pot. So in the beginning, you have like a N2 atomic oxygen inside the thermosphere is all balanced because the weight is different, and the N2 stayed low. Now you have this heating going on, it's like stirring the pot. So now the N2 goes up and changes the ratio between the atomic oxygen and N2 molecules. So this one is a O2 N2 ratio, and what it does is you have more N2 goes up, and even though the heating just happened instantaneously, this thing will linger on a little bit. At the beginning, it was more or less, and as this interaction happens, you can see more N2 goes up, and you can see that it affects a large area. If this just changes ratio, what happens is when you change the ratio, it eats out the ionosphere. So the ions interact with the N2 and it reduce ionosphere. So ionosphere is there. It itself does not affect the communications and GPS signals. But when you have a lot of changes going on, it does affect those systems in there. So the model purpose is trying to have a more accurate prediction, how we can getting this correctly predict how the ionosphere is going to change, how the O2 N2 ratio will change during the storm event. Let's see. So how do we calculate the geoheatings? And we need a few parameters to calculate geoheatings. One is electron density in the ionosphere, and one actually is neutral winds, and it's a neutral wind and the ion drift velocity difference square that generate the heat. And so these are the parameters we need in order to calculate the geoheatings. And the model need to put in those parameters. And what we need is to have observation to validate the models. Model can simulate whatever it wants, but you want to know whether these numbers in the model are correct or not. And you need observations of these parameters. And so in terms of ion drift, there's a system in place called a SuperDAM, which is a high-frequency radar. It has a coverage both in the Arctic and the Antarctic region, and it covers the ion drift in there. In terms of electron densities, you have a small and a larger infrastructure in the region. And in the Arctic region, we have incoherent scatter radars, which is a large facility at the Resolute. And then you also have a network of ionosons, the Canadian put together various places in there. So these two parameters are covered pretty well. But in terms of neutral winds, and it's only like two flags here, and one in Resolute, one in Eureka, and so we're really falling behind in terms of coverage of these neutral wind coverages in there. And the instrument looked like this, and the Fabry-Perot interferometer is an optical remote sensing device. It measures thermospheric winds by sensing the light emitting by by the atomic oxygens emitting. So you can measure the Doppler shift of the light due to the neutral winds in the thermosphere. You can see it on the ground, but as you can see that this instrument is not small. It's not like a GPS and the magnetometer you can put in the field easily. So I need a little bit bigger infrastructure in order to field those kind of instruments. And usually what we do is we measure the four directions, and north, south, east, west, and the vertical. And the opposite directions, the Doppler shifts are opposite. So you can figure out, that which way the directions the winds are flowing. You need to know the two components, meridional, which is north-south, and the zonal winds, and we're looking up. And this is the spectrometer, the interferometer create these kind of rings, and it's a very sensitive instrument. We can measure like 1 meter per second kind of accuracy. And here's the one in Eureka, when they're with a collaboration with my colleagues in New Brunswick. This one's actually is a smaller device I have built for this project. And this is one in Resolute. So we did some comparisons of the winds we observed and with a model. And at the Eureka, the agreements are very nice. On the top are the meridional winds and the north-south winds. At the bottom is the east-west winds, called the zonal winds. And that'd be nice. And at the Resolute, and the observation seem to be taking a shortcut here, and that the model seems to be predicting even larger winds, and we don't understand why that is happening at this moment. And the problem is that you have the model give you a wrong kind of winds, then your Joule heating is not correct. And when your Joule heating is not correct, because Joule heating also affects the winds feedback. You have Joule heating create pressure gradients, and so you're at the beginning you're wrong, and your Joule heating is wrong, and whatever you create a variation due to the Joule heating is also incorrect. So there's a problem with that. So we did some scatter comparisons between the Eureka FPI and our model, and the Eureka is pretty nice, and they're 90% agree with each other. But when you go to Resolute, you like the model is having like a 30% larger winds in there. So obviously you have a problem with the model, and we don't know what the problem is yet. And not only look at the Arctic region, we're also collaborating with my Korean colleagues in Antarctic. We have instruments in Jambogo Station, and this is the instrument look like. And those of you who haven't been there, Mount Melbourne there, and this is a nice building they built for space weather, and it's a nice modern station there. And so the assessment of the model here, and at the very high latitudes, and the model seems to be doing pretty good job. And at some 80-degree magnetic latitudes, the disagreement can be as large as 40%, and it certainly generated a lot of problems. Joule heating is not correct, and whatever the errors you have generated from the Joule heating is also incorrect. So my solution for this problem is modest request. It's not a huge request. In the Arctic region, I'm thinking about maybe we can add one more station in there. Since my instrument doesn't go to the field, doesn't like to stay in the cold, and like to have a AC controlled environment. So I know there's a station, there's a building in Chile somewhere, and this building there, and then maybe perhaps we can add one more station there. and then we'll have a 3 instrument inside the polar cap, and still fewer than other instrument, but I think it's a improvement nevertheless over there. And I also maybe collaborate with my Canadian colleagues, putting one more station in somewhere in Alberta. I have an instrument there in Boulder here. So in Antarctic, and I'm thinking about maybe we can add in a few more, few more stations here, and we have one, as I supported one at the South Pole, and we also have one at McMurdo as well, and the Jambogo is over here, and I myself running another instrument over in King Sejong station. Will be down very quickly. And I'm hoping adding one more station, maybe at one more instrument at Concordia someplace, and maybe at the west. How do we go to west? And I'm thinking about maybe we should do an upgrade on this AGO instrument, which is been Antarctic for many years, and we certainly need more power, more general purpose, and have a higher data speed, perhaps, and not only speaking for myself, there's a group of scientists there interested in going to west. That if you have a more beef up Eagle observatory can deploy somewhere in the East Antarctic, not have to be exactly at the west, maybe Union Glacier, any other places, can be very helpful for my purposes. So in summary, we certainly need more instruments, and in Arctic region, as I said, hopefully you can add one more station, the Thule station. Maybe in Antarctic, maybe adding one more in the East Antarctic region, maybe west, other places, and like to see upgrade version of Eagle sometime.